I realized we have 40 minutes, and I actually love Q&A more than I like talking. And then I also realized that we have 60 slides. So we're going to do this Peach Kucha style, 20 seconds per slide. So just be ready if you want to take photos. We're going to kind of go through it pretty quickly. I didn't realize that Rapids has grown so big that we have so many libraries and we have so much to talk about. But we're going to try to keep it succinct. There's also a booth out there if you want to come up afterwards and ask us any questions as well. So with that, so data processing is evolving. When data processing first started, it was kind of this big revolution of Hadoop. And it just allowed people to use these commodity CPUs to really do scale-out computation. And it was this paradigm of reading from disk, doing something, writing to disk, and kind of iterating through that. And then Spark came around. And Spark said, you know what, if you can put all of that in memory and keep most of it in memory the whole process, you get these massive speed-ups. And then also, MapReduce was a difficult paradigm to use, and so Spark was really focused on ease of use and making it a lot simpler for people to do massive scale computation. But even with something like Spark, doing just kind of aggregations, this is the New York City taxi data, and what we see is we get CPU limited very quickly. And so you can go to Mark's blog about the New York City taxi data, and he really kind of explains where the real bottleneck today in big data computing is at the CPU. If we try to push all of it there, we're going to hit limitations. And this is really kind of the motivation for what we were doing in Rapids. And so how can we do better? We wanted to, focus on full data science workflows. If we accelerated a part of it, we basically just hit Amdahl's law, where you only do accelerate one part of it. Even if you accelerate it a lot, you're only going to get a certain amount of a speed up end to end. And we wanted to be Pythonic. Data scientists love Python. Python is growing. I'll talk more about this tomorrow morning in the opening talk. And we really wanted to meet developers where they were. We wanted to provide them a simple Pythonic interface. We wanted to do end-to-end, and we wanted to be performant as people expected from GPUs. And so when we initially started this almost 3 years ago, our first kind of exploration into GPU computing, we wanted to go from MapD, now OmniSci, an in-memory GPU database, to Graphistry, a GPU-accelerated graph visualization library. And while both of them could do things orders of magnitude faster than their CPU counterparts, copying and converting data so they could talk to each other killed all performance. And so what we realized very quickly is we needed to have standards. We needed to build Rapids and this GPU Open Analytics Initiative ecosystem in a way where data could seamlessly go from GPU app to GPU app, staying on the GPU, because MIM copies are essentially like the bane of any type of performance. And so at the same time, Apache Arrow was really kind of kicking off. And so there's just some great work that's going on in this ecosystem. There's Dremio, which is here. Wes has Ursa Labs. And what Arrow really wanted to do is remove the computational waste of serializing and deserializing data. And so if everything could talk to everything through a natural columnar interface, we just get a lot more performance. Now this columnar interface is really important because it also works not only on the CPU, but it also works on the GPU. So the same columnar interface. So all we have to do is pay that copy penalty to move the data to the GPU, but we don't have to convert the data. And so just like Arrow on the CPU, it connects all these things like Pandas and Drill and Parquet. It does the same thing on the GPU, where we can read in Parquet directly into a GPU. We can then turn that into Arrow. We can do computation on it. I can pass that to my machine learning library, my graph analytics library, et cetera. So with that, we basically went from early stages of GPU apps and data science of reading and writing to system memory to Rapids, where we keep things on the GPU as long as possible. We have common formats, and it really allows us to have a much more accelerated ecosystem. And so I'm going to talk with you, I'm going to talk about Rapids for a little bit. I'm going to talk about cuML and cuGraph specifically, and then Keith's going to talk about cuDF and Dask and where we're going with Rapids. So cuML. Data's growing, and the keynote tomorrow is going to talk about kind of user experience and iterations. And he had a really great Twitter kind of series of tweets. I don't know what you call a series of tweets, but anyway, he had a series of tweets, and one of them was talking about how do you win a Kaggle competition. It's this combination of iterations, performance, and trying out different models. And what we realized is this is kind of the core thing that we wanted to empower data scientists with cuML. People need to iterate faster. You can get to an answer in a certain amount of time, but if you want to get to an optimal answer, if you want to get to a Kaggle-winning answer, it's really around iterations. It's not around the absolute speed of your library. Speed is important, performance is important, but it's really about how often you can iterate. And so there's this combination of user experience and performance, and we wanted to really kind of blend the two of them together. And so what we did was we wanted to follow the scikit-learn API, follow it as close as possible so people don't have to learn something new. So they still get the same ease of use that they get with scikit-learn, but it's built on it's built on these C++ APIs, which we can then GPU accelerate with CUDA. And then on our side, we're like, you know what? Instead of building these algorithms one by one and writing them, exclusively for each other, why don't we break down these algorithms into classes of algorithms, classes of problems, which then you can turn into primitives. And so we have solvers, we have distance matrix calculations. We have all these different ML primitives, as we're calling them, and we can layer them together and we can build an algorithm, and then we wrap that algorithm with Python that follows the scikit-learn API. So the end user gets a really fast algorithm, and under the hood is all this GPU acceleration, and even how we develop is fast because we take a very modular approach. And so a little bit more about the primitives. There's a combination of linear algebra, sparse, random, statistics, distance metrics, solvers, decomposition, and we're continuing to build more primitives. As we add more machine learning libraries, we realize that we just need to continue building more primitives to make it easier for these algorithms to be created. And there's a list of different algorithms that we're accelerating. Today we have decision trees, linear regressions, logistics, KNN. We're working on some Bayesian inference. We have common filtering, k-means, dbScan, PCA, UMAP, and we are also working on some time series models as well. And so at the high level, this is kind of how we divide the world up. There's the Python side where we use Dask to do distributed machine learning, both data and model parallel. And then we have model parallelism in our CUDA C++ layer. And then we have all the primitives and GPU communication at the bottom. So think things like MPI, Nickel 2, et cetera. And so this is just kind of the stack in another way. CUDA libraries, so think cuBLAS, cuSolver, cuRAND, the ML primitives, the cuML algorithms. We have our Python layer, and then we bind that to Python. So here's an example of clustering. Really not much to say. It's pretty straightforward. Simple scikit-learn-like interface, and you're calling things like fit and predict, and you're off to the races. Here's some benchmarks of some of our machine learning algorithms. TSVD, as we scale to larger data, we're getting 8 to 10x improvement, about 20x on PCA. dbScan is about 15x. And UMAP is actually one of my favorite new algorithms. We just released this in RAPIDS 0.6. This was the first algorithm that someone outside of NVIDIA blogged on. And so I know people are like, okay, that's not that exciting. But it was really exciting as a core contributor to the library and working on it, that people are now not only using RAPIDS, but they're now also like evangelizing about it and telling other people. And so the blog was basically showing how they get about a 15x improvement using UMAP for some type of clustering application. And it was just really exciting that people are using it more, filing issues, and they're exciting other people about the library. So we're really excited about the addition of UMAP, the fact that it generated its own blog in a few days. And I think UMAP is just a really cool algorithm in general. And so quick show of hands. Who's familiar with TSNE? Okay, and now a show of hands of who's familiar with UMAP. Okay, so UMAP is essentially, it's an algorithm that's like TSNE, except it keeps some thoughts about how data is connected, how close things are to each other. And so when you're doing the dimensionality reduction, it doesn't completely throw away all of the information that you have about your data. So it gives you slightly better embeddings. It's faster. It's more rooted in pure math theory. And so the combination of different things that it does with different manifold properties and how it's designed, it gives you similar or better results in TSNE at a fraction of the time. And this is where I like to talk about tech as magic. As a person who's used TSNE for years in econometric spaces, and now having something that is faster than TSNE, slightly more meaningful in its clustering, and now it's another 15x faster because we can put it on the GPU. You're literally getting two orders of magnitude, slightly more, to do the exact same thing that you've always done, and it's better. And I just think that's just really magical. So anyway, I love Leland. I'm really excited that he designed the UMAP algorithm. He has a really great talk on it from last year's SciPy. If you're not familiar with the UMAP, please check it out. Go follow Leland. He's much smarter than I am. He's a really great guy. So cuML. We started here in 0.1. We didn't have much. It wasn't very impressive. Here is where we are today. We're really excited about the progress. You can do GLM on multiple GPUs. You can do KNN on multiple GPUs. We have all the things that you see on the left. And this is where we plan to go in the next release or two. So in 0.7, 0.8, we're going to add some more multi-GPU libraries. And sorry, I thought I had another slide here. I guess I got cut out. By the end of the year, we're going to have this matrix even further filled out. So cuGraph. Prior to NVIDIA, prior to the White House, I led a lab in cybersecurity. I'm really passionate about cybersecurity. I love cybersecurity. Cybersecurity is a connected problem. Graph analytics is actually how I ended up at NVIDIA. We met Graph History back in 2014. We were really impressed with how fast they could do these really massive graphs for threat hunting. And so then we wanted to start doing things like PageRank and breadth first search and triangle counting to enrich those graphs so we could use them in our modeling to find anomalies. And that's when we bought our first GPU server with 2 GPUs. And what we realized was things like GraphX were almost 200 times slower than things like BlazeGraph and some of the other graph analytics libraries like GUNROCK. And so, NVGraph is something that NVIDIA started a while back. And what NVGraph is, it was really kind of low-level CUDA C++ graph implementations to help people build graph libraries faster. And then there was there were some other projects at the time that were really inspirational, like GUNROCK out of UC Davis, which I used before I joined NVIDIA. And then we were working with Georgia Tech at the time on Hornet, also known as Hornet's Nest for some of their algorithms. And so, we've been working on graph analytics for a while, and there's all this academic research on it. And when I joined NVIDIA, I wanted to make sure that we were unifying this. So some graph algorithm packages has like a frontier-based approach. Some have a linear algebra-based approach. And so really the unification of all these things is what's really exciting about cuGraph. And so here's just a few examples of some data sets. They're fairly large data sets in some respects. They're not that large in others. But a few hundred million nodes, lower billion edge graphs. And these are the speedups we get when we compare it to something like NetworkX. And I know what people are saying. NetworkX is a pure Python library. This is no kind of knock on NetworkX. We love NetworkX. It's a great library. But what we wanted to do was follow the NetworkX API and use basically CUDA acceleration under the hood to really kind of speed things up. I think most people would be really happy to do things 1,000 times faster. And so with a 32 gigabyte V100, single and dual GPUs on just a normal workstation, here's some other performance we've seen with things like PageRank. And this is like kind of my last really excited moment. Here is a PageRank benchmark, but this is actually comparing to 8-core cloud instances of Spark GraphX versus just one RTX 8000. And so a lot of times when people think about GPUs, they think about the cost of them, and granted GPUs are more expensive than a CPU. But when you think about how many CPUs you have to use, so 80 cores essentially can do PageRank in about 1,500 seconds. where, I think that was around 3 or 4 seconds on a single RTX 8000. You can think about all the networking, the setting up a Spark cluster, or you can think about just taking one RTX 1000, putting it in a workstation, and getting a result. And so today we have Jacquard, weighted Jacquard, similarity, PageRank, Louvain, SSSP, breadth first search, and we're continuing to add more algorithms to our cuGraph package. And so later this year, PageRank is very important. It's kind of the cornerstone of cybersecurity. So our goal is to have a multi-GPU, multi-node implementation of PageRank by the end of the year. We want to have multi-GPU for some of the larger graph analytics algorithms that we use in cybersecurity. We have a very vibrant cybersecurity team, and I'm really excited about all the work they're doing. So we want to make sure that we're supporting them with the right algorithms. And so, yeah, graph's really important. If you're a NetworkX user, show of hands who uses NetworkX. Cool. Go try out cuGraph. Just go get any GPU, and you'll be very happy. And so a little bit more. So actually, I want to go back. Plans for the rest of the year, future work. There's this thing called Hornet. I talked about it earlier from Georgia Tech. The thing about Hornet that's a little bit different than most graph packages, most graphs are static graphs. Hornet was designed from the very beginning to be a dynamic graph structure. And so imagine being able to do tens of millions of upserts a second into a graph. So all these different events, just streaming them into a GPU, updating it, and then doing real-time graph analytics, where you're kind of like remembering the past to converge on these graph properties a lot faster. And so we're really excited about Hornet as well, and working with the Hornet team to really kind of bridge streaming and static graph. And so here's some of Hornet's insertion performance. It's really fast at updating graphs. And so I don't know how many people have ever used things in the big data space about streaming graph inserts, but it's phenomenal. I mean, it's more than pretty impressive. It's just amazing that some of the work that's coming out of Georgia Tech. And then GUNROCK. So we've been working with John Owens for a while, and John Owens has been leading the GUNROCK team for about 5-6 years now at UC Davis. They are kind of the standard for distributed large-scale graph analytics algorithms. And one of our goals is, GUNROCK is a very massive code base. We want to help them make it more modular and get that integrated into cuGraph. So all of these multi-GPU algorithms, we can have them using things like CUDA 10, CUDA 10.1, the latest architectures, whether it's Turing or Volta, and just really kind of continue to work with them to make sure that we're having this cohesive one graph package that balances both static and dynamic, both single GPU and multi-GPU. And with that, I'm going to turn it over to Keith. Here you go.
All right, thanks, Josh. So I'm going to talk about cuDF. And kind of in building cuDF, one of the first things that kind of people asked us is, do we really need to GPU accelerate ETL? And we talked to a lot of different people about kind of their pain points in working with ETL today and kind of what their workflow was. And we quickly found out that the average data scientist is spending 90+% of their time in basically just slicing and dicing and cleaning their data. And we also found out that because their current tools don't allow them to really work at the speed of thought, that they've developed a caffeine addiction from basically kicking off a job and being like, oh, this is going to go run for 30 minutes. I might as well go grab a cup of coffee. And then I forgot to add this feature, or I had a small issue in my code. Crap, I need to re-kick this off. All right, let's go grab another cup of coffee, and so on. And so that really led us towards building this cuDF library. And so at its core, cuDF is really a low-level kind of C++ and CUDA implementations to be able to use the hardware as effectively as possible, along with Python bindings on top of it to make it look and feel like pandas, which data scientists are used to using and are comfortable using today. And so the lower-level library called libcuDF It has all of like it has a full C++ API that users can use, and then has all of the CUDA kernel implementations underneath. It exposes things like sharing data frames across processes using something called CUDA inter-process communication handles, and then has kind of the things that you would typically expect in a data frame library, like element-wise math operations, sorting, joins, group bys, et cetera, type operations. And then in the Python side, it kind of has all the things that you're used to with pandas, like integration into the rest of the PyData ecosystem. And so you can like interoperate on things like NumPy arrays and PyArrow structures and similar. And then we also heavily use a library called Numba. For those of you unfamiliar with Numba, I believe they are giving a talk at this conference. So Numba is a just-in-time code compiler for Python. And so we use it heavily within cuDF to allow users to essentially write user-defined functions in kind of naive, pure Python, and then it just-in-time compiles that to vectorized GPU code under the hood. And so what this means for you as an end user is kind of instead of using like .apply and pandas and having it execute in pure Python and be really slow, that you can do the same function and it actually gets compiled down to GPU code and gets run at essentially the speed of hardware. And then this is all run on top of the Apache Arrow data structure. And so integrating with kind of the rest of the big data ecosystem and the PyData ecosystem is really as simple as just copying memory to or from the GPU. But it's not just about cuDF. ETL is all about how do I handle this large amount of data that allows me to make intelligent decisions based on it. And so if we were limited to just the scale of a single GPU, that doesn't solve most problems that users have. And so we're heavily leveraging Dask as well, and we have a library called Dask cuDF. So Dask, I'm sure there's a talk at Anaconda on Dask, but for those of you who aren't familiar, Dask is very kind of native to the Python ecosystem. And Dask is a kind of general purpose distributed scheduler and computation engine that allows you to kind of scale your Python workload to either use all of the cores in your laptop or workstation to running on like thousands of nodes in a supercomputing cluster. And so for us in kind of cuDF and in RAPIDS, Dask is really the backbone that allows us to scale our workloads both up on a machine to use all of the GPUs available in the machine and to scale out across more machines. And what's great for us is that the more that we follow the Pandas API, and we're trying to follow it as closely as possible, the fewer the changes that needs to be made to Dask data frame in order to leverage cuDF under the hood for that. And so what this means is that basically any kind of code base that you have today in using Dask data frame, it should be an almost drop-in replacement to just GPU accelerate it using Dask cuDF. But there's some performance concerns with doing that. By kind of normally, Dask uses TCP to ship data between workers and across machines. We're working with both the Dask community and then with another open source project called OpenUCX that basically allows us to take advantage of hardware communication fast paths. And so what this means is that in a machine, if I'm communicating between two GPUs, I don't want to essentially copy data off the GPU and then turn it into something that I can send over a socket to just move it back onto the GPU. I want to take advantage of either NVLink, which is essentially like a hardware interconnect between two GPUs, or just copy data over the PCI Express bus. OpenUCX will allow us to do that on a single machine. And then for multiple machines, it will allow us to essentially just send raw memory buffers across things like InfiniBand network cards and like 100 gig Ethernet with Rocky, and basically take advantage of all the hardware available in these systems, while for an end user, they get to just work at the high level that they're comfortable and familiar working with. And then kind of one of the big things really excited about as of recently, so in 0.6, we just merged our initial string support into cuDF and Dask cuDF. And so we have some initial element-wise operations, so things like splits, finds, extracts, string concatenation, typecasting. That all just landed in 0.6. There is some regular expression support as well. It all runs on the GPU. Please go try it. Let us know what's broken. We're really excited by this. We also support things like group bys and joins. And so NV Strings was originally closed source. We recently open sourced it, and this will now allow, we're going to be working with IBM and other vendors to figure out how we can properly support PowerPC for Rapids as well. And in the next release, in the next couple releases, we're going to be working on things like a GPU-accelerated CSV writer, and then kind of additional operations that follow the Pandas API as well, and then a more generalized and efficient categorical column implementation. And so kind of I talked about a GPU-accelerated CSV writer, but what I want to really talk about is some of the work that we've done as far as accelerating file reading. And when you talk about kind of file I/O and file reading, people don't think like, oh, that's something that a GPU will accelerate. People normally think like, oh, I need to do some like big, dense matrix multiplies. GPUs are good at that. It turns out that GPUs are actually really good at accelerating I/O just because I/O turns into a memory throughput problem of how fast can I scan over these bytes multiple times. And GPUs have a ton of memory bandwidth. And so what this translates into are really big speedups for like typical file formats. So we, as of 0.6, we have near feature parity with Pandas for CSV reading. Pandas, it typically maxes out around 50 megabytes a second or so. What we've seen thus far in our CSV reader is you'll typically get around a gigabyte a second or so, and we haven't really spent much time on optimization, and there's still a lot of room for improvement there. Coming in the next release, it was actually just merged into the development branch around a week and a half, 2 weeks ago. We have a GPU-accelerated Parquet reader as well. So it will follow the API of Pandas. The current implementation, they're seeing a more than 10x speed up over Pandas, which uses the Apache Arrow, PyArrow reader under the hood. And kind of some of the way that we're able to get this speed up is by handling all of the decompression and parsing on the GPU. That basically there is a single mem copy to get all of the bytes over to the GPU, and then all subsequent scans of that data are in GPU memory, which is just like an order of magnitude faster than host memory. And then kind of what the team is also working on is an ORC reader as well that will handle decompression and kind of have a very similar API to the Parquet reader. And we're going to try to land that in this upcoming release. If it doesn't land in this next release, it will be in the following release. But you know, ETL isn't just data frames. And so we're doing work in the n-dimensional array space as well. And so in the Python ecosystem, it turns out there's about 15 different GPU-accelerated n-dimensional array libraries. And so if Rapids was to just build another n-dimensional array library and try to say, this is the standard, all of a sudden we would just have 16 different GPU-accelerated array libraries. So what we've really been working towards are building standards for interoperability within the community. And so kind of a couple of the things we've been working with is the CUDA array interface, which was spearheaded by the Numba developers. That's basically a standard metadata description for arrays on the GPU. And so it will expose things like, here's the pointer to my data, here's my data type, here are the strides, here's the shape of the array. And DLPack is kind of, it's at a lower level, it's a C library, and it's more kind of deep learning framework focused, but it exposes similar things. But the end goal is to allow these different GPU array libraries to share memory between them without having to copy or convert data back and forth. And so kind of before there was DLPack or CUDA array interface, if I wanted to say, do some kind of operations using CuPy and then hand that off to PyTorch to then train a network on, I needed to basically copy the data back to a NumPy array in host to then create a PyTorch CUDA tensor that is the exact same memory format as my original CuPy array. And so I'm happy to announce in 0.6, we integrated both the CUDA array interface and DLPack in Rapids in cuDF. And so this means that kind of the deep learning frameworks that support DLPack, the libraries that support CUDA array interface, you can go to and from Rapids without having to leave the GPU. And we're going to continue to work with this ecosystem to try to enable these libraries to share memory effectively. So the other thing, we're working with kind of different GPU-accelerated array libraries with Dask to allow using them underneath Dask array. So similar to how we're kind of plugging in cuDF underneath Dask data frame. We are working to plug in GPU array libraries under Dask array to allow you to kind of scale your array computing, both up and out within GPU boxes. And so there's, I'm not going to play them now, but there's a couple videos here. Definitely check them out. Matt Rockland may be showing one or two of these videos in his talk, I'm not sure, but definitely check these out. They're really cool videos to show you kind of the difference that GPUs can make in your computing workload. And just like kind of quick example of kind of what GPUs can allow you to do as far as scaling up. I don't remember the exact workload here, but using all of the cores available in the system, so 40 CPU cores, it was a dual 20-core system. It took like 11 minutes and 30 seconds to run this workload. With a single GPU, we can bring that down to 1 minute and 37 seconds. And then if we scale to 8 GPUs, we can get it down to 19 seconds. And then kind of as well, so I believe this was run on GCP in kind of some of their VMs. And then kind of in addition to that, in scaling out, if you kind of scale out and use a whole lot of GPUs available to you, so I believe this was 20 instances with 4 P100s each, you can actually get to the point where you can run an operation on 3.2 petabytes in less than 1 hour, which is kind of a crazy number. And in order to do that using CPUs, you would have to use a very large number of CPUs. And so, you know, the road to 1.0. So Rapids is fast. We've kind of been trying, part of the goal of Rapids is to take advantage of hardware to accelerate workloads. You know, we're typically getting a 10 to 25x improvement, but you know, there's tons of inefficiencies and tons of places that we could still be even faster. That there's a lot of places where we have overhead of just-in-time compilation where we shouldn't, that we're not caching things where we should be, and we haven't really spent a lot of time in optimizing the kernels quite yet. And that's because the bigger goal of Rapids is we could provide you all the speed in the world, but if it's not friendly to data scientists and data engineers, it's a non-starter. And so kind of the goal for us is that we want to deliver the performance of GPU-accelerated CUDA, but we need to deliver the comfort of the Python data science ecosystem in order for it to benefit end users. And so kind of the road to 1.0, some of the things that our team is working on right now, so things like windows and rolling window functions, further improving UDFs, further improving string support, and then kind of looking towards more domain-specific things like preprocessors, words to vec, geospatial functions, and kind of some additional statistical functions. And then we're starting to work kind of more closely with the Numba developers to kind of improve our integration with Numba as well as enhance Numba with kind of additional functionality. And then kind of, so in this chart here, you can see at the left, these are the issues within cuDF over time. And if I can go back here for a second, you can see that as our library has developed more and more, we're just starting to get more and more feature requests, which is really exciting for us because that means users are actually using the library and want to see more things that they can use within the library. And so kind of part of that is also we need to do a better job of kind of better error messages and better error handling. That right now we're using CFFI, which doesn't allow us to raise errors from the C++ side, and so we need to move to Python to do that. And we need to kind of just provide a better end user experience as far as when things fail, they need to fail in a way that it guides the users to a solution instead of these kind of cryptic messages that it just makes them kind of throw up their hands and say, well, I'm blocked. And kind of, as you can see here, we're doing a pretty good job of maintaining the number of kind of bugs and issues that we're seeing as development goes, which is kind of healthy as we continue development moving forward towards 1.0. Also, Rapids is kind of being integrated in every major cloud platform. So if you're primarily a cloud user, go to the cloud, use Rapids is compatible with every major cloud. We strongly encourage you, use it wherever you use GPUs today. And then kind of, so we've talked a lot about Rapids, what it does, how it does it. Rapids is available today. You can go, it's all open source. You can go check it out on GitHub. It's github.com/rapidsi. We also provide Conda packages, PyPy packages, and then containers as well, where you can download the container from either Docker Hub or NGC. If you run into issues, please let us know. We're really trying our best with packaging. The other thing, so with the 0.6 release, we actually just reworked our documentation as well. So there's a new doc site here, docs.rapids.ai. The team, I know Mike gave a talk earlier about GPU CI. He helped a ton with this doc site, so I want to give a shout out to Mike that this is awesome. It's a lot easier to use, better than ever. There's a quick getting started section on cuDF. I really encourage you, check it out. If you're familiar with Pandas, it should be really easy to get up and running with cuDF, that it should basically look and feel exactly as you're used to today with a different import statement. And so with that, join the movement. Everyone can help. So we work closely with other open source communities. So the Apache Arrow community, RAPIDS, GPU Open Analytics Initiative, anything as far as integrations, feedback, documentation, issues, pull requests, literally anything is more than welcome. We love to hear feedback from the end users, especially if you run into issues. It really helps us to basically prioritize our development so that we can enable you as end users to use these libraries. And so with that, thank you, and I think we'll take any questions.